our speaker this evening, Dr. Larry Nittler. To my great surprise, Dr. Nittler knew it, but I didn't know it until just recently. This is the third time he's presenting to the NCA.
Oh.
His first presentation was in December 1997, back when the NCA meetings were on the campus of the National Institutes of Health. And he spoke to us again in February 2004 at our present location. So he's our all-time champion speaker.
Third time's a charm.
Yeah. He earned a bachelor's in physics from Cornell and a PhD from Washington University in St. Louis. And he was a staff scientist at Goddard Space Flight Center for 2 years. And then he joined the Carnegie Institution of Washington, D.C., his present position. He's a cosmochemist and a planetary scientist. And he does research on the evolution of stars and on topics that are really quite closely related to that. Namely, the production of all of the chemical elements that were not present immediately after the Big Bang. Also on interstellar and interplanetary dust, on meteorites, and on the formation and evolution of planets. And his research is both in the laboratory and using data from spacecraft, obtained by spacecraft. In the laboratory, he focuses on the isotopic and mineralogical properties of microscopic extraterrestrial materials, including presolar grains in meteorites, interplanetary dust particles, and samples returned by spacecraft, including the samples of the solar wind that were returned by the Genesis mission, and the samples of comet Will 2 that were returned by the Stardust missions. He also in the spacecraft-based remote sensing, he uses geochemical data. He led the analysis of X-ray fluorescence data from the near-Earth asteroid rendezvous mission, which orbited asteroid Eros in 2000 and 2001. And he also led the analysis of the X-ray fluorescence data from the Messenger mission, which orbited Mercury from 2011 to 2015. He was also the deputy principal investigator for Messenger. He's on the science team for the European Space Agency, Japan Space Agency EPI Colombo mission, which was launched last year and is currently on its way to Mercury. And he's a participating scientist on the Japanese Space Institute's Hayabusa 2 asteroid sample return mission. So we're actually going to get a piece of an asteroid back to Earth. He received the Nier Prize of the Meteoritical Society in 2001, which is a very distinguished honor, and became a fellow of that same society in 2010, which is another major honor. Asteroid 5992 Nittler is named in his honor, and he's very versatile. He's also a jazz pianist and composer.
Thank you. I'd like to thank John for the invitation and for dinner, which is very nice. And I was a lot younger the first time I spoke to you. Some of you might have been as well. But I'm assuming everyone in this room remembers everything I said in the last two talks, so I don't need to repeat anything. No, so I'm gonna sort of most of my talks are gonna be background material to discuss this kind of cute result that we published earlier this year about this very interesting little object we found inside a meteorite. So I'm gonna start at the sort of big picture, well, not big picture by astronomical standards, but by local living on the planet. This is the next bigger picture once you get off the Earth, which is more or less what the solar system looks like today. I mean, scale's not quite right and all that, but, and usually all the planets are not quite so lined up. But of course, this is more or less the architecture of the solar system. We have somewhere between 8 and 100 planets, depending on how you define the word planet, and minor planets, and comets, and a well-established middle-aged star. But This is what it looked like 4.5 billion years ago. This is, of course, a very, very famous image from a few years ago from the ALMA radio telescope array in Chile I think that's HL Tau, so of a forming, very, very, very young planetary system. This is an artist's rendition of what one of these stars would look like, or the sun when it's forming. And basically, as a star molecular cloud collapses to form a star, it has to conserve angular momentum. It always has some to begin with, and that physics forces it to end up accreting largely through a disk. So you have a large amount of material in this sort of rotating pancake-shaped thing of gas and dust, through which gas goes down and builds the star. And in the meantime also builds planets as sort of a side effect of the process of turning dust and gas into a star. And so that's an observation. These are more older observations from the Hubble Space Telescope of such disks around forming stars, where you see the disk because it's dark, because it blocks all the light from behind. And these are in the Orion Nebula, which is a stellar nursery where lots of new stars are being born today. So 4.57 billion years ago, this is what the solar system looked like. And the question is, one of the big questions I work on and many of my colleagues work on, and it's a big driver of people who study meteorites in general, and also many astronomers, of course, who study disks and young stars, is how do we go from here to here? What are the steps to go from something that looks like this to something that looks like a mature planetary system? Like I said, we know that planets are born in these disks. I've already shown some pictures of gas and dust. I'm not sure what I've got here. Okay. So here I'm just going to step through, again, schematically what's going on here. You have a molecular cloud, just a giant cloud of gas and dust out in between the stars in the galaxy. And for reasons that are not particularly well understood, at some point bits of parts of these molecular clouds decide to collapse under their own weight and form new stars. And you end up in this, again, because of conservation of angular momentum, you end up with a forming star and this disk called a protoplanetary disk. And it starts out as a hot cloud of mostly gas and some dust. And then as this disk cools, some of the gas atoms condense to form new dust grains. And these dust grains start floating around and sticking to each other and grow bigger and bigger and end up making small bodies. And there are problems in every single step, things we do not understand in every step of this process, even though we think this is the basic process and have very good evidence that this is the process that occurs. And you make small bodies, and then you make the small bodies start building into larger bodies and planets, and you build up a core of a bunch of Earth masses out where Jupiter is, and it's so massive it starts sucking in gas from the disk, and you can grow gas giant planets very, very quickly by that. And closer to the sun, you just have small bodies, but they're growing and growing, until eventually you have planets, and the disk goes away, and you end up with a system like this. Now, what we know in our solar system is that we've ended up with 4 rocky planets, 4 gas giants or ice giants, depending on what you call Uranus and Neptune, and a lot of small stuff. We have asteroids, and we have icy bodies in the outer solar system, Pluto size, Sedna size, down to comet size. And all of these small bodies are basically leftovers, fragments of the process of building the planets, which in turn are just leftovers in the process of building the star. It's just that not everything from the disk could fall into the star, so some of it survived in this form. These asteroids and Kuiper belt objects, or trans-Neptunian objects, are very, very, because they didn't grow to full planet size, they trap a memory of what was going on in these very, very early stages. They never turned into planets that melted and recrystallized and had billions of years of evolution, like the Earth, for example. And so they preserve a record of this very, very early stages, so they're of great interest to study. They're really leftovers. They contain a dynamical record, which I'll get into a little bit later, and a chemical fossil record of the early stages of solar system history. The grains, the minerals that are there, the types of materials there keep a record of the physical and chemical conditions of their formation. So we can infer timescales and temperatures and pressures and so on, and try and rebuild the whole history of the early solar system on very small scales, but to better understand things. And this is very complementary to the work of astronomers who use telescopes to study disks around new stars, which are looking at things today, or very recently because of the speed of light, looking at processes happening today, but there's only so much resolution you can have with a telescope, only so much you can do. On our end, we can use instruments in the laboratory to study things with incredibly small detail, and but only small bits and pieces of what was left over. And so, of course, the two disciplines were trying to come together to understand this in a holistic way. But again, so specifically I'm talking about studying these small bodies in the solar system. How can we study these small primitive bodies in the solar system? And traditionally, of course, we can study things in space the way we've always studied things in space, by looking at them, and that's astronomy. And this is just example, for example, of abundances of certain different molecules and different comets as the comets get closer and closer to the sun. And so you can do this kind of thing to understand the volatile ices in comets. These are reflectance spectra of different asteroids, so you can use this to try and determine what the mineralogy is of different types of asteroids and understand them. I'm not going to talk any more about either of those, but it's examples of what we can do for these primitive bodies. Increasingly, we can use spacecraft to go visit these things and make measurements remotely, using all kinds of fancy instruments to try and understand them. And this is, of course, what's on my shirt too. This is the asteroid Ryugu, which the Japanese mission Hayabusa 2 just spent 1.5 years exploring this asteroid. And twice it went down to the surface and scooped up some material, and now it's on its way back to Earth with some dust from this particular asteroid. And in about a year, it's going to be back on Earth, and in the middle of 2021, we'll be looking at these samples in our laboratories, and I'm hoping to have some in my lab, to directly measure what's going on in a carbonaceous asteroid. So that's very exciting. This is an asteroid called Tempel 1 that the Deep Impact spacecraft went to, and it threw a big ball of copper at it and made a big explosion in a crater, and then used instruments to look at what was thrown off to learn about what comets are like. This is MU-69 that just got a new name that I can't remember, based on a local Native American tribe or language from this area, because this was discovered by scientists from Maryland. And this, of course, just about a year ago, the New Horizons spacecraft flew by this body. It's a Kuiper Belt object, and boy, does it look weird. And icy, cold things. So we can visit these things. Some cases bring stuff back from these things. And a lot of what I do is wait for things to come to us. Because all of this stuff, these things hit each other and make dust and make rocks. And a lot of those gradually get pulled into the sun, into the gravity well of the sun. And if they happen to be crossing Earth's path as Earth going around the sun, they might hit the Earth. And if they're really, really big, we don't like them, and they make dinosaurs go extinct and cause all kinds of problems. If they're really small, we might see them come down and think, oh, that's a pretty shooting star. But a lot of them will get to the surface of the Earth, and we can analyze them in the laboratory. And in this way, directly sample these types of bodies, even though we never know exactly which body, say a meteorite or a piece of dust comes from. By looking at large numbers, the advantage is we can look at large numbers of these and understand statistically their properties, and on very, very, very small scales. And the rest of my talk is going to be giving examples of some of the things we know about these, and then a nice little story, again, that we published earlier this year based on one of these meteorites. But this is the famous fireball of Chelyabinsk, which was this large meteorite that fell in Russia a few years ago and broke every window in the city of Chelyabinsk, and taught the rest of the world that every single person in Russia has a dashboard camera filming. So there's just tremendous numbers of videos of people of this fireball, because people just were constantly filming what's going on through their dashboards. So we have a lot of information about that. So again, I study meteorites, rocks from space. This is an engraving of a famous meteorite fall called Ensisheim from the late 1400s. I'm not sure how accurate this is, a view of it, but there it is. But this was hundreds of years before scientists really accepted that rocks fell from space. It took a long time to establish that, but by the early 1800s, most people accepted that meteorites were actually rocks from outer space. People knew that rocks fell from the sky, but I think before, leading hypothesis before, say, 1800s was that they were forming by some weird interaction of lightning and clouds making these rocks. And it was really only in the late 1700s that people finally said, yeah, okay, we believe it, they come from space. And we know a lot more now. For example, this was a very famous meteorite, again taking advantage of the fact that people like to take videos of things. This fell in New York in 1992, and this is the fireball as it came down the sky. And I think it'll show a map eventually where it came across. It came across the northeastern seaboard in the United States on a Friday evening in the fall when everybody was at high school football games videotaping their kids out on the field. So there's tons and tons and tons of video footage of this meteorite fireball. And there's videos you can see where you see a little bit of the fireball, and then it goes back to the football game, and then it goes back up to the fireball. But the really, and then also then landed in Peekskill, New York, and smashed the front end of this woman's car that apparently had a blue book value of a few $100s. It was a real clunker, and she sold the meteorite in the car to a dealer for $30,000, so she was okay with the damage. I saw this on display in France last year. They had a big meteorite exhibit at the Paris Museum of Natural History, and included this car out front. You could see it. It was pretty cool, and the meteorite. But this kind of footage is very, very valuable. And now there's places all over the world where they've set up fireball networks to automatically get footage of meteorite falls when they come. Because if you can reconstruct the whole path as it comes in the sky, you can reconstruct the path before it was in the atmosphere and then figure out where these things are from. Oh, that's not my next slide, but I'll get back to that. Oh, no, that is. No, it isn't. I just don't understand. It's showing me current slides and things. Okay, anyway. I'll stop worrying about that. Before I get to where are they from, where are they found? Meteorites fall all over the Earth. But there are good places to find, so if you happen to see one fall, you can find it. Meteorites that have been around for a while are much easier to find in some places than others, and specifically in deserts, because deserts are very dry. If a meteorite falls out here and no one sees it fall or finds it, in a few decades it's going to be completely disintegrated from the water. It's going to weather it away and you would never recognize it as a meteorite. But on a dry desert like the Sahara or Antarctica, they just can last tens of thousands of years. And even in Antarctica, there's also glaciation concentration mechanisms that move the meteorites to sort of concentrate them in front of mountain ranges, so where it's easy to find them. In addition to the fact that Antarctica has a mile-thick layer of ice above the ground, so it's actually, if you find a rock, it's more likely it fell from outer space than it came up through all that ice. So there's a lot of reasons Antarctica is good. That's a picture of me 19 years ago this week. I realized when I was putting this talk together. So I did an expedition to Antarctica. NASA sends people there every year to collect meteorites, and you spend several weeks living in a tent, and you ride around on a snowmobile looking for black dots. That's your job, is looking for black dots. And if you find one, chances are it's a meteorite. Sometimes you find coal, because there's coal in Antarctica, but mostly it's meteorites. And so, again, that's me. That's a meteorite that we just found in the snow, and that's me collecting it. And that's pretty cool. But going back to where are they from, we can use those fireball networks and places where you can reconstruct the orbit, and that's been done now. This is an old slide when there were only 3 or 4 of them, or 5, and there's a lot more now. But all of them, when you do this, you can get back, you reconstruct the orbit, and you find out that they originated in the asteroid belt. So these these meteorites are from asteroids. And we know that very well from this. We also now know it from the previous sample return missions. And like I said, that's Ryugu, that's Matilda that was visited by Near, that's Eros that was visited by Near, and that's Ida.
Yeah, because of
Dactyl,
Dactyl.
which was the first moon asteroid discovered. There's a lot more of those too now. But again, these are all pictures taken with spacecraft, so we have a good idea, a very good idea about asteroids. And I should have put Vesca on there, I suppose, in series, now that they've been visited by spacecraft. But that's where meteorites are from. When we look at them up close, meteorites come in different flavors. Most of them are what we call chondrites. I'll come back to these because that's what I'm going to be talking about. Achondrites are volcanic rocks that are not from the Earth. They are igneous rocks that form from melting and recrystallizing of rocks on another parent body, another planet. Most of them come from the planet Vesta, the dwarf planet Vesta, the asteroid Vesta. I don't know what its classification. Big rock out in the asteroid belt.
Yeah.
Some of them come from Mars, some of them come from the moon. Some of them come from bodies we do not know where they come from. I'm not going to talk about these, but they're really interesting. Iron meteorites, which is what a lot of people think of when they think meteorites, because lots of museums have giant iron meteorites, are very, very rare, but they are so strong that they survive. Big ones survive the atmospheric entry much better than big rocks. So if a big chondrite hits the atmosphere, it breaks into a million small chondrites, and you end up with a strewn field and of lots of them. Iron meteorites will also break up, but you'll have much bigger chunks. These are from the cores of planets that melted and differentiated. Planets, by planet I mean asteroid, in the very early solar system, very, very small planets, that then got completely broken apart. And so that was the metal that was at the center of an asteroid. Chondrites are what I'm interested in. They are basically grab bags, sedimentary rocks from the protoplanetary disk. They're made up of very fine scale dust. They're called chondrites because they have things called chondrules in them that are sort of millimeter-sized balls of silicate. And in between those is micron-sized dust particles. And this stuff all was forming in that disk, as I was saying, came together, accreted together as the first step in planet formation, and never got big enough to melt. So these are the things when I say we have a fossil record of the early solar system. This is what we study. We know from radioactive age dating that some of the things in these chondrites, these little white, weird-looking things, which are called calcium aluminum-rich inclusions, those are the oldest things anyone's ever dated using radioactive isotopes, and they are 4.567.3 billion years old. And these objects those are the oldest things formed. So that's commonly taken as the time zero of the solar system. They were probably the first things to form, or among the first things to form in this whole process of gas to dust to planets. Yes?
What's the cementing agent that holds all the grains together?
It's, in some cases it's carbon. There's very fine amounts of carbon in there. But more, it's just that there was enough gravitational pressure that they stuck together, and there's some sort of solid state diffusion between adjacent grains. But some of them are insanely porous. You try and break it apart and it just breaks into dust. So they're not that well held together. Yeah.
Yeah, I think did I hear right that one of these iron meteorites actually was used commercially? They actually mined the iron?
Yeah, they made swords out of them.
Historically, people have used iron meteorites as a source of iron. I don't know about commercialization.
Well, that's what I mean.
Yeah, I mean, people have used them for anvils and weapons and things, I think, to prehistoric times. Probably the first source of real metallic iron for people before they learned how to, mine ore and stuff. So.
Oh, okay.
Yeah, and there's interesting stories where they found. There was an interesting paper a couple of years ago of a famous sword in China that they discovered was made from a meteorite. It was an ancient, couple thousand-year-old sword that was very famous, and some people did some chemical analysis and discovered it was made from an iron meteorite, which was kind of neat.
Yeah, the Behringers, I think, mined Behringer meteorite.
Tried to.
Yeah, so they own the meteorite carrier, hoping to make money from it. That's the big crater in Arizona near Flagstaff, which was from an iron meteorite fall 50,000 years ago, and it's an amazing place if you haven't been there. It's really cool to see a hole in the ground made by a meteorite. And you can still, if you go around, you can find little bits of meteorite, but they never made money off it mining. They wanted to.
They never found much iron either.
Right. But they've been very generous to the Meteoritical Society, which is the professional society of people who study meteorites, and that they've given a lot of money and sponsor travel awards for students to conferences and this kind of thing. So we like the Behringer family. So I'm going to talk a lot about my work, or not a lot, but some of the work I'm going to be talking about that I do is all based on isotopes. And to remind people what isotopes are, I know everyone knows, but I'll remind, is that the atom, of course, is made of a nucleus made out of protons and neutrons, and surrounded by a cloud of electrons. And isotopes are different versions of the same chemical element that have different numbers of neutrons. So every carbon atom has 6 protons in its nucleus. If it's a neutral atom, it also has 6 electrons. But about 1 out of every 90 carbon atoms on the Earth has an extra neutron and is called carbon-13. And then, so the solar system on Earth, it's about 89, 12 carbon atoms to every carbon-13 atom. But geochemists and cosmochemists, we can now use mass spectrometers to measure the isotope ratios of the elements, and those isotope ratios can change for a large number of processes. A lot of chemical processes occur in a mass-dependent way, so the reaction favors one isotope slightly more than another. Radioactive decay can perturb things by huge amounts, and other nuclear reactions can cause very large changes to isotope ratios. So I'm going to be showing isotope data, so I just wanted to remind you of what isotopes were. And in fact, I'm going to jump now to some of the important characteristics, relevant characteristics of meteorites, of chondrites, the primitive meteorites, relevant to the rest of my story. And I'm going to start with oxygen isotopes. Oxygen is the most abundant element after hydrogen and helium. And it is, of course, extremely important. It's also one of the most abundant elements in rocks and in our bodies and everywhere. And it turns out to be extremely important in meteorite studies, and this is based on discoveries that were started in the early 1970s. So I'm going to spend a couple seconds here on this plot. Geochemists use these weird delta values. So this is a lot of fields. What these are oxygen isotope ratios. Almost all oxygen is oxygen 16, 8 protons, 8 neutrons. But about 1 out of 500 of them is an 18, and about 1 out of every 2,500 is an O17. So these are rare isotopes. So instead of plotting it as 0.002 or 0.0004, we plot things in deviations. And so these values are the part per thousand deviation from the Earth, basically. So the Earth sits at 0, 0, and it's defined as SMO, as standard mean ocean water, and that's some vial of ocean water sitting in somebody's lab somewhere. And it has been defined as the standard for these measurements. So the Earth sits at 0, 0, and what you note, so 10 is 10 parts per thousand, or 1%. So if you plot here, that means you have 1% more oxygen 18 than the Earth does. So these are small variations, but very, very important ones. Because what you see is these different types of meteorites all have their own little field here. So Ci is one type of meteorite, Cm is another, Cv is another, LH, LL, R, these are all different, and they are all different, and you can't easily go from here to here on this plot through normal chemistry. So something was weird in the very, very forming stages of the solar system to cause this variability in oxygen isotopes. Even though it doesn't look very big, but these are on planetary scale. I mean, the Earth and Moon are on this line, but, you know, these are asteroid-sized things or planet-sized things, and they're different. So you're averaging over huge amounts of material and still be very different. Now I'm going to zoom out. This is most of the known meteorites. But when we look at the Sun looks very different. So we didn't know this for most of recorded history. This is only a result from the last decade when we went to send a spacecraft to sit in space and collect the solar wind, which are ions streaming out of the sun, embed them in materials, bring them back to Earth and measure them, and then we were able to measure what the sun's oxygen isotope composition is. I'm sorry, the purple's a little hard to see, but the solar wind is here. You have to correct for some things in the instrument and discover that the sun almost certainly sits right here. And that's at about 5% enriched in O16 relative to everything else. This box is the plot I showed you a minute ago. So now this is much bigger. The sun is at 5%, 50 per mil. CAIs are those little white things I showed you early on that are the oldest things in the solar system, and they seem to be between the sun and almost everything in the planets. And then a few years ago, somebody discovered this stuff here, which they named cosmic symplectite, which is a kind of strange word, but they were first calling it new PCP, for new poorly characterized phase, which was an even worse name, so this is better. Science is weird. But this was in a very, very primitive, unusual, unique meteorite called ACFR 094, found in the Sahara Desert. They found this material that's a weird mixture of iron oxide and iron sulfide, and discovered it had this composition way up here, like 20% more oxygen 16, like 15 to 20% more oxygen, less oxygen 16 than the Earth and planets, and even more than the sun. So we now think what's going on here that makes all this mixture is that the sun was here. There was probably a water reservoir. Water was one of the most abundant molecules in this disk, in the gas phase, and also in ice. And for reasons we don't understand, and I won't get into it unless people really want to know, but we have some chemical ideas as to why, the water in the outer solar system sat up here, and the planets formed in this disk by mixing of the starting stuff, which is down here, and the water up here, and everything ended up averaging in this small region. But small differences in how much of each thing got mixed in led to those variations. So that's interesting. But for the rest of my talk, the important thing is we have this weird material up here that we think is associated with the outer solar system. And
What is TFL?
Oh, I'm sorry, I should have been clear. That is the terrestrial fractionation line. That means anything with Earth composition can lie on that line. The chemical fractionation, diffusion, evaporation, melting can move you up and down on a line like that, but cannot move you on this line. So that's again how we know this is different. That these variations are not just from diffusion or some kind of chemical reaction.
And what is COS?
That's short for this cosmic symplectite, this weird stuff. So it's just this weird inclusions they found in this meteorite. And it's the only place in a meteorite, other than the stuff I'm going to show you later, that's been found with this composition. No other meteorite has shown it. Oh yeah, that's right. So that's oxygen. Also relevant to my talk, my story, is that meteorites have carbon in them. And not a lot of carbon, but a couple of percent of carbon, up to 1-2%. Of these primitive meteorites is carbon, and that carbon is in organic molecules, and it's not there are some simple ones like amino acids and carboxylic acids and things that are very, very important and may be important for the origin of life on Earth, and we do lots of study, but most of it's in this weird tar-like macromolecular stuff that we're trying to understand. Very, very complicated. We don't know where it formed, we don't know how it formed, but it's there in the couple percent level of meteorites. And these meteorites were part of the building blocks of the Earth, including in the late stages, so they probably did deliver an awful lot of the carbon that eventually became life on Earth. So that's why we're trying to study and understand the carbon before it hit the Earth to find out what the original building blocks of what became life was. But that's not what I'm talking about today. Again, these are now isotope maps. This is data we published quite a while ago now. Little chunks of organic matter we had extracted from a meteorite and mapped it with our ion probe and found that on these very small scales, this is a 2 micrometer spot, so that's 2 millionths of a meter. This thing is tiny, tiny, tiny. We see there's variations in the deuterium to hydrogen ratio. That's what this is about, where some spots have 20 times as much deuterium as the Earth, and some spots have the same amount as the Earth. Similarly, you have variations in the composition of nitrogen isotopes. This is nitrogen 15 over nitrogen 14. And it's very, very variable. So this stuff probably formed throughout the solar system under weird conditions. We're trying to work this out. But the isotope ratios are a good tracer of what the material is like, even if we don't understand why it has those ratios. Different meteorites have their own signature of these isotope ratios. Just like in oxygen isotopes, they have their own signature. This is what I talked about the last 2 times I gave talks here, though that was, again, 22 years ago and 15 years ago. So I'll forgive you if you don't remember. I had more hair and less gut at the time. Let's see, this is a cartoon I made many, many years ago now about presolar grains, which are my great scientific love. I spent a lot of time on these things. And the basic idea behind them is that before there was even a molecular cloud to form a solar system, there were previous generations of stars, like supernovae and AGB stars, that at the end of their lives made dust. And so, you see a planetary nebula, what that is dust that was made in an AGB star now being lit up by the central radiation from the central white dwarf. And so this dust grains, and supernovae make dust and inject this stuff into the interstellar medium. And that dust got mixed up with everything else from all the other stars and all the gas to make this molecular cloud that eventually formed the protoplanetary disk. And we now, of course, as I said before, we have asteroids and comets that preserve stuff from the disk. And we get those stuff on the Earth in the form of meteorites and interplanetary dust particles, which I'll talk about in a sec. And we've known now for 30 years that when you look in very, very fine detail in these meteorites, you find some dust grains that are these dust grains from supernovae and AGB stars, that these are older than the solar system, and they're a way of studying stars in the laboratory. How do we know that? Because that seems completely insane. Again, these are micron in size. They're very, very small. They're very rare. And again, the answer comes from these isotope ratios. So remember I said that almost everything in the solar system, again, I'm sorry, it's really hard to see, but there's a line here, a red line, at 89. Almost everything in the solar system sits right here on this plot. Carbon 12 to 13 ratio, maybe 80 to 100 at most, but really a smaller range. Similarly, this is basically the same oxygen isotope plot I showed before. When you put it on a scale, these aren't delta values, these aren't these part per thousand variations, these are absolute ratios over many orders of magnitude. These are log scales. So huge variations. Of course, the whole solar system sits in there. When we look at the grains that we measure in the meteorites, instead of 89, the meteorite might, or the grain, this is silicon carbide, so that's a type of mineral, might have a ratio of 3 or 1,000. And these ratios, I mean, that's completely out of this world, literally out of the solar system. Those ratios are way too crazy. Similarly, the oxygen isotope ratios, instead of 2,500, 16 to 17 atoms, you might have 100, and huge variations in these things. And these are oxide minerals, things like sapphire, like aluminum oxide, and silicates, these blue things. There's olivine, pyroxene, stuff you see on the Earth. These are grains that formed inside AGB stars 5 billion years ago or something. Survived millions of years, billions of years of evolution, and only to be ruthlessly destroyed in my lab to understand where they formed. But these variations are way too large. The reason we know they are presolar grains, stellar grains from stars, is that these isotope variations cannot be explained by any sort of standard physical or chemical process. They require nuclear reactions. It's really nuclear reactions that make huge perturbations in the isotope ratios. And the place in the cosmos where nuclear reactions are occurring is in the interiors of stars. That is where the elements are made, turned into other things, because you've at very, very high temperatures, these atoms, these nuclei smash into each other and become new things. And in fact, we can, in some cases, compare the grain data to astronomical observations. So this yellow thing now is a histogram of carbon isotopes measured in carbon-rich AGB stars. So carbon-rich stars at the end of their life, stars like a couple times the mass of the sun, say, at the end of their life become carbon-rich and make silicon carbide, and it looks exactly like the grains we find. Similarly, you can measure the oxygen isotopes in some oxygen-rich AGB stars, and they overlap. The errors are big because you're doing this with spectroscopes, and it's very complicated. But we can say these grains come from stars. And so it's pretty cool. Again, it's not the purpose of the talk, and I've talked about them here before, and there's lots of papers, and I'm working with some people to probably write a book in the next year or so on them. But they basically are pristine bits of stars that have survived huge numbers of processes. So they've been used now for 30 years to study stellar nucleosynthesis and the evolution of chemical elements in the galaxy, how dust evolves in the interstellar medium, what are the source materials of the solar system, and processes in the early solar system. And that's a little relevant for what I'm going to talk about now. Specifically for this talk, the important thing, we've been using them not only to study stars, but to study the asteroids that we find that the meteorites come from. And that's because the amount of these grains varies from meteorite to meteorite. And we think this is reflecting them being sensitive to processes happening on the asteroids, like small levels of heating and small levels of aqueous alteration. Some of the meteorites, many of the meteorites, accreted with ice that then melted and interacted with the dust. So the dust is not exactly what it was in the nebula, and is like clay minerals and so on. And it turns out that presolar grains get modified by this as well. And so this is what we find in silicon carbide. The details aren't important. The point is that in these different meteorites, the silicon carbide isn't about all the same amount, because silicon carbide is not easily destroyed. It's really tough. Presolar silicates are very, very sensitive to this kind of aqueous processing and heating. So when we look at different meteorites, we see different amounts of these things. And the most primitive meteorites have sort of 300 parts per million. They're still really rare. It's a very small part of the meteorite that are these presolar grains. Most of the stuff in the meteorite formed in the solar system. It's a tiny bit. And we see different types of meteorites have different amounts, ranging from, I'll show you another plot later, that even some of these get down to a few parts per million. But no more than 200 or 300 parts per million. So I'm going to switch from meteorites. How am I doing? Okay.
A range, or should we just look at the range?
Oh, that's a good. It's actually just look at the number up here. For these are individual meteorites. It's not the best plot in that way. In that it should be a point with an error bar. So copied it out of a plot paper, but it's not necessarily the best way to put it. But I'm going to switch away from meteorites now. So those are the important characteristics of the chondrite meteorites, which come from asteroids. We know they come from asteroids because of the fireball reconstruction and from sample return, and we're going to find out more when the Hayabusa 2 samples come back. Now I'm going to switch to other extraterrestrial materials that we study, in particular IDPs. So interplanetary dust particles are essentially the zodiacal dust you see out there when it hits the Earth. And since the 70s, NASA has flown aircraft in the stratosphere and put little metal plates on the wing coated in oil to collect these dust. And if a dust particle comes on and hits that plate, it sticks like a fly sticking to fly paper. And then you can bring them down to Earth. And it turns out that it's flying at like 17 kilometers altitude. And that's high enough that there's very little dust from the surface of the Earth gets up that high. And again, most of the dust that you find is either coming from outer space or has been deposited in the stratosphere by rocket exhaust. So we find little aluminum oxide spheres that we think are from rocket exhaust from rocket launches. But we also find things like this, and they're just very, very tiny meteorites. This is a 1 micrometer scale bar. So these things are a few microns, maybe 10, 20, 30 microns at most across, and they're very, very fine grained. They're made up of all these little stuff. And for a number of reasons, we can tell that they're both from asteroids and comets, but that a large fraction of them are from comets, and especially these ones that look really fluffy. They're these little fragile aggregates of tiny, 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 tiny dust particles. And, but again, we have modern instrumentation. We can study these in great detail and learn something about them. So that's a way to study comets in the laboratory. One important thing is they're made up of both glass and crystals. These different grains are different compositions. We find these long, skinny crystals of enstatite, which is a magnesium silicate, that we call whiskers, and we find these very unusual little objects called GEMS, which is an acronym for glass with embedded metal and sulfides. These are tiny, tiny, 100 nanometer, 200 nanometer balls of glass, silica glass, that also have even tinier little blebs. These little dark spots are tiny little grains of metal, iron nickel sulfide. We don't know where these formed, we don't know how these formed, but they seem to have been an important component of the dust that formed the comets. So they probably formed in the solar system very, very early on, and we're trying to understand them. But they're almost entirely only found in interplanetary dust particles, in very small meteorites, not in the chondrite meteorites I told you about. This is two other things about IDPs. They have much more presolar grains than the meteorites. So this is that same plot I showed you before, where the highest value in meteorites is maybe, this is old too, that's out of date. So really the highest value is about 250 parts per million in meteorites, and in IDPs they go up to 1%. So they're much more primitive. These things have seen less processing than even the unprocessed asteroids that form the meteorites. This is an IDP that was measured by a lab in England 5 years ago, and they found a little region here. It's hard to see the plot, but basically this is here on this oxygen isotope plot, and that's essentially 200, that's where this cosmic symplectite stuff was. So this shows that in addition to that one meteorite, it's also seen in IDPs, which again are thought to come from comets. Another type of IDP-like material are things called micrometeorites in Antarctica, Antarctic Micrometeorites. These are typically the same size as IDPs, up to a few hundred microns in diameter. People find them by going down to Antarctica and melting ice and melting snow and filtering the water and painstakingly go through the filters and find these little tiny particles. They have to filter out all the penguin feathers and exhaust from nearby, snowmobiles and stuff. But they do find these particles. A lot of them, if they're in the 200, 300 micron scale, that's a typical size of the particle you see burning up in the atmosphere to make a shooting star. It's a typical size hitting the Earth. Those are very largely completely melted. But if you find the smaller ones, the ones smaller than 100 microns, they're typically in pretty good shape, and they look a lot like, some of them look a lot like the IDPs that were collected in the atmosphere, though these were found in snow in Antarctica. And there's a really, really interesting subset of these are things called ultracarbonaceous micrometeorites, or UCAMs, which are mostly made of carbon, but have other minerals and silicates in them. And these were found to be really interesting for a number of reasons. One, they had extremely isotopically anomalous hydrogen in some cases. Some of them do, some of them don't. They have these gems, these weird silicon grains with the tiny bits of metal in them. What does that mean? We don't know. They have organic matter. This is infrared spectroscopy. Without worrying about the details, the point is that they have some of this organic matter, have very, very high abundances of nitrogen. And these authors argued that these things are forming either in comets or in the surfaces of Kuiper belt objects like Pluto, where the radiation from space interacts with the local ices and makes these organics. We don't know where they're from, but they're definitely from the very outer solar system. And I think, I'm not going to talk anything about the VIL-2 samples that were brought back by Stardust, except that they largely look like the other cometary samples, but they have some things that look more like meteorites, so it's kind of confusing. But there were some very serious technical challenges with analyzing these samples from the way they were collected that caused some real biases. So even though they're the samples we directly brought back from a comet, it's very hard to interpret them, and I'm not going to talk about them too much, or at all now. I'm going to now get to the main point of my talk. The main point of the talk was to give you this background. So this is from the title. This is a paper we published in Nature Astronomy early in the year in April that I led, but with a number of people. Rhonda Stroud is a physicist at the Naval Research Laboratory who did some of a bunch of the important work in here. And I think she spoke into this group, but again, it might have been 10 or 15 years ago. Joseph Trigo Rodriguez is a scientist in Barcelona who found this object, or his student, Carlos Moyana, found this object that I'm going to talk about, and brought it to Washington, D.C. to study in my lab. And then the others all contributed in various ways. And what we studied was a chondrite, a chondritic meteorite, from a group called the CR chondrites. There are all these different classifications. It's totally irrelevant, except to say CR chondrites are among the most primitive. They seem to be some of the least altered meteorites in our collections. They have reasonably high abundances of presolar grains, but not that high. Some of them are in the 200s, some of them are lower, in these parts per million. They have isotopically anomalous nitrogen, more anomalous than some of the other meteorite groups. So there's some evidence that these are very primitive, and that's why we were studying them. It was like we were targeting these meteorites, and my colleague Joseph in Spain had requested a sample of this particular meteorite, LAP 02342, to study it. And so this is a meteorite found in Antarctica in 2002 in a place called the LaPaz Icefield. It's small, it's about 42 grams. That's the entire meteorite as it was found. We got a thin section of it, so this is sawed-off section, cut really thin for us to study in our labs. So that's maybe a centimeter across, and you can see these roundish objects are the chondrules, and in between is this fine-grained matrix, and the bright, these gray things are metal grains. It's interesting. And even on this scale, 1 centimeter was found to be quite heterogeneous, that some parts of this had seen more interaction with water than other parts, so it was an interesting meteorite. And this student, Carlos, used a scanning electron microscope to map out the elemental abundances across this whole section. And mostly he was looking at magnesium and silicon and aluminum and things like that. But he looked at the map of carbon because it was automatically made. And normally you don't pay much attention to carbon because these things are embedded in epoxy. So there's tons of carbon usually around. So you see the green is where all the carbon is in the epoxy. And there's a big blob of epoxy there. But when you zoom in here, it turns out he noticed, oh, there's a weird little patch. You can see these sharp veins. That's epoxy and cracks in the meteorite. But there's this fuzzy little patch of carbon was unusual. Hadn't seen something like that. So we looked at it up close. And we named it the carbon-rich class. So this is about 1/10 of a millimeter across, 100 microns. It's sort of heart-shaped, and it's mostly carbon. This is more than 70% carbon. All this dark stuff is carbon. We've never seen something like this in a meteorite before, in this type of meteorite before. It's not pure carbon. There's other silicates here and so on. These are elemental maps, again from the electron microscope. So bright means more carbon. So you can see it's very bright in carbon, dark in oxygen, though there's oxygen grains within the carbon. You can also see it's rich in sodium, and it's a little harder to see with the sulfur because there's also sulfides outside it. But it's a very chemically unusual object. We don't really see these things in meteorites, or haven't before. So we're like, oh, well, we should study this in more detail. So we decided to apply all of our whole array of analytical techniques that we use to study these things. So this is sort of astronomy in a laboratory. So our telescopes are really mass spectrometers and microscopes and things. And what I do is something called SIMS, secondary ion mass spectrometry, where I shoot a beam of ions at the sample. It knocks atoms off, and then we can put them through a mass spectrometer to weigh them and determine their isotopes and elements. Transmission electron microscopy, you send a beam of, say, 1 to 200 electron volt electrons focused to a very, very fine point. You send it through a sample, a thin sample, and based on how the electrons interact with the material, you can learn a lot about what its crystal structure is, what its chemical composition is. And I'll also show some data we got from a synchrotron facility at Lawrence Berkeley National Lab, where we send a very, very high intense beam of X-rays focused to a very small spot through a sample, and look at how the sample absorbs the X-rays to learn something about the chemical functionality, and I'll talk about that too. So now I'm going to jump to the results we found for this object. We found presolar grains, my great love. The white symbols are, this is this oxygen isotope plot again, and the white symbols are the grains that were found before, and these red ones were ones we found in this meteorite. They look the same, they're in the same range as most of the previous ones. But when we look at the abundances of them, it turns out we did a lot of searching outside the clast and a lot in the clast, and we found that the clast itself had huge amounts of presolar grains compared to the matrix. Don't worry about SRR, but basically the matrix had very low abundances of presolar grains at the low end of this class of chondrite, but this clast had values that went much higher. Now the error bar is very big because we didn't find too many grains, but it showed that the class seems to be different from this and seems to overlap with IDPs. Again, these samples from comets. So we're like, that's interesting. But we were mapping in oxygen isotopes to find these, using the SIMS to map the oxygen isotopes. And we found something really interesting. We found that throughout the class, but especially along the edge of the class, this is now a color map of the oxygen isotope ratio. You can see at the upper edge of this class, there's this bright stuff going all along it. Turns out this has this composition up here, which is near this COS stuff. So this is the first time in a different meteorite than Astro 94 that we found something like this, and it sits very close to that. So is it related to that? We think it is. We think it's related to this outer solar system water. We did the SEM on it and discovered that it's made of sodium and sulfur. You get this purple color here because it's made of sodium and sulfur in this map. And so we've now determined from other measurements that it's a sulfate, that it's a sodium sulfate mineral, which is, I don't think, ever been seen in a meteorite before, which is different from what you see in this other meteorite, except that both sulfates and this magnetite stuff are made by interaction of water with other minerals. So it's consistent with both of them being formed by reaction of dust with water that has this very unusual isotope signature. Again, from the outer solar system. We also mapped out the organic matter, and these are isotope maps over parts of this glass. That's carbon. That's the amount of deuterium to hydrogen. I don't want to get into details except to say that the range we see is very similar to what's seen. These are now individual IDP measurements of deuterium to hydrogen. Each one of these is a different IDP. UCAM spread something like this, and this class is very similar to what's seen in IDPs. The meteorites themselves typically have higher deuterium than the IDPs, and we don't really understand that. But the class looks like an IDP. This is the X-ray data I was talking about we did at the synchrotron out in Berkeley. So, giant facility to make a tiny beam of X-rays. And, hit the wrong button.
It'll go away.
Okay, it'll go away before I keystone it to death.
Yeah.
Basically what we're looking at here is how many X-rays are absorbed as a function of energy. Will it go away? Well, I won't press anything again.
I say.
And what you see is that, as you said, that X-rays of, say, 280 electron volts go right through the sample. And this is looking at carbon in the matrix and carbon in the class. But at, say, 300, they get blocked by a whole huge amount. And that's because the carbon atoms are absorbing X-rays here. And right in between, at this edge, you see these little wiggles. Each one of those corresponds to a different carbon molecule that absorbs at that given X-ray. So this little blob means you have benzene-like carbon there. And all three of these things have that. And these are these other molecules that have more oxygen things. The only thing important here is that this is what the matrix looks like, the typical organic matter in the meteorite. And that looks very much like what we've seen in lots of other meteorites. The clast, when we're deep in the interior of the clast, looks quite different. And you'll have to, that you can see that here, this one's much higher than this one. Here, this one's about the same as that one, and that one's in between. So the chemistry is different in it. And again, the important thing is that it's different, not what the details are. And I want to show a little bit again now. This is transmission electron microscope data. So now we're in very small scales. These are element maps and transmission electron micrographs. This is a blob of carbon in the matrix. And we see silicates and glass and carbonates and sulfides, but we don't see any sulfates like we see in the clast. When we look at the clast, we see a lot of carbon. These are all false color maps, and this is a micron or something. This is very, very, very high resolution data. And you see all the red is where the carbon is, the oxygen's in between, there's sulfides everywhere, these green are sulfides. There's sodium sulfate, this pink stuff, and there's all these interesting things going on. we see there's holes everywhere. This thing's very, very porous. The rest of the meteorite's compact, but this stuff is very, very porous, full of holes, and full of these weird minerals. And we also even see gems, these little glass things with the sulfides in them and metals. And this is a blow-up of these gem grains. This is, again, what it looked like in an IDP. Now, the imaging mode is different here, where the internal sulfides look bright here and look dark here. But you can see it's the same texture. You have this little ball of glass full of it with these little inclusions in it. And to remind you, these are things that before have been seen in... Sorry, we'll go away eventually. What we see is, again, that they really haven't been seen in meteorites, but are pretty common in these IDPs and these ultracarbonaceous micrometeorites that come from the outer solar system. I have only a few more slides, and I'll just skip that. So this is the summary of what the clast is. And the key point is that it's different. We found this thing, it looked different, it is different from everything else in the meteorite. It's made of carbon, very, very highly porous carbon. It's got this high abundance of presolar grains. It's got different organic matter. It's got this very unusual sulfate minerals with oxygen-16 pore, and these gems. So what we believe had to have happened is that as the parent body of the CR chondrite was forming, this asteroid, and is forming from accretion of dust, getting bigger and bigger and bigger, this thing just happened to be nearby. This object was not where it should have been. And that, in fact, most of the meteorites are pretty homogeneous in their types of material that are there. And somehow this thing wandered in from somewhere else in the solar system and just said, okay, I'll land there, and then got buried in other dust that eventually grew into this asteroid that, billions and billions of years later got knocked off the asteroid and hit the Earth and was found in Antarctica. But this object doesn't look like anything like meteorites, but it looks a lot like these ultracarbonaceous Antarctic micrometeorites. It's got very similar, all of these properties overlap with UCAMs. And again, thought to be cometary or outer solar system in origin, but we found this in a meteorite. So the meteorites formed much farther in, a few astronomical units. Comets formed, tens, 20s of astronomical units away from the sun. How did it get there? What's going on here? So our basic idea of the history of this thing is that originally it accreted way, way out in the disk as a little mishmash of ice particles that have this O16, a weird oxygen isotope composition, carbon particles and silicates, accreting probably as one of the original building blocks of a comet-type material, type planetesimal. And then it either came directly into the inner part of the solar system and became part of a carbonaceous asteroid as it was growing, or it first accreted into a body out in the outer solar system. That's comet 67P.
She was not German code.
Thank you. Sometimes I can say it, sometimes I cannot. That was visited by the Rosetta spacecraft. So it could have originally accreted into a different body and then been emitted or ejected by an impact or something, and then found its way into the inner solar system, if this formed a long time before this did. We think the carbonaceous asteroids formed a few million years after some of the other asteroids. We don't have any real constraint on when the comets formed and the parent bodies of them. But in order to make it look like what it looks now, at some point it had to have heated, because the ices had to melt and then react with the silicates to make the sulfate and slightly alter some of the minerals. But even when it did that and altered stuff, it didn't alter things as much as you would expect, and we think that's because the carbon protected things. So although the water made these sulfates, it never destroyed the presolar grains or oxidized the gems away. So we think the carbon protected them, and this is like a unique time capsule of outer solar system chemistry. I should mention that it looks like it's one of these ultracarbonaceous Antarctic meteorites. Nobody's seen sodium sulfates in these Antarctic micrometeorites, but no one would, because it's an extremely water-soluble mineral. And these things were found by melting of ice. We didn't have to melt ice to find this thing. We just had to find it inside a rock. So that was hard in its own way. But it's a way of it's a fossil of things that we can't see if we find them in the Arctic. So it's like a time capsule of early solar system chemistry that was protected by the meteorite. We don't know where this heating took place, and this is basically the end of what my story is. We know it had to have been heated. It could have been heated while it was moving inward before it hit there. It could have been heated by an impact or something on the parent body. It could have been heated in the asteroid itself. We know the parent body of this meteorite also underwent some slight heating and melting of ice. So there's no way we can disentangle this with just the one. But of course, now that we know that it exists, we're now doing a concentrated search to find more objects like these in primitive meteorites, because if we found a bunch, then we can maybe do statistical tests and start thinking of other interesting things we could do on them to try and understand them. But I really wanted this as a case study of, you know, one interesting object in a meteorite that we can use to trace much bigger processes of planet formation. And it's telling us, and I think I have some, oh, yeah, thanks at the bottom, but just sort of summary is that the fact that we find this cometary-like clast in a meteorite indicates that there was some transport from very far out in the solar system into the inner part of the solar system during the first few million years of planetary formation. We already knew things went the other way from the stardust results, which I didn't get to, but there's definitely high-temperature stuff that formed in the inner solar system in Cometville 2. Now this is evidence of stuff forming in the comet region and coming in. So it's important for people who try to understand how material moves in protoplanetary disks. Again, this is what I was talking about a second ago. We can preserve these fragile materials like sulfates in the meteorite where we wouldn't in Antarctica. And we just need to find more of these materials. And of course, we're going to look for this in the samples that come back from Bennu and Ryugu by the OSIRIS-REx and Hayabusa 2 missions. And I have talked for a very long time, so forgive me, an hour or so. And I will take any more questions. Thank you.
Has anyone radioactively dated a so-called pre-solar grain? Or do you just say they're pre-solar because of the weird chemistry?
We say they're presolar because of their isotope ratios that indicate they could not have formed in the solar system.
Right.
People
I think
have
it's safe.
tried to find ways to radioactively date them. They do not have enough uranium or lead in them to do that. The way people have been trying to do it is with something called cosmic ray exposure ages. And essentially, if the thing's floating around in interstellar space for a long time, occasionally galactic cosmic rays will hit the grain and interact, have a nuclear reaction, and say, break apart a silicon atom and make a neon-21 atom. Or break apart a carbon atom and make a lithium atom. So people have measured noble gases like helium and neon isotopes and lithium isotopes in some of these silicon carbide grains. And then from the amount they see, they have to use a model of the cosmic ray spectrum. They have to make assumptions, calculate how long these things were in interstellar space. And when they do that,
kind of gives you a crappy date, is what you're saying.
you get a crappy date, but they have these isotopes in them, and they have enough of these that they had to have been exposed in interstellar space for anywhere from tens to hundreds of millions of years. But the uncertainty is big, but they have enough of them to know that it could not have been done in the solar system. So we do know they're presolar from this, even though the numbers are a little iffy. But we're still trying to find better ways to do it, and that's kind of the holy grail of this research.
How are you storing these samples that you have? Do you have a refrigerator or something?
We keep them in desiccator cabinets. We don't have to keep them cold because they weren't kept cold when they were collected or when they fell. In principle, the Antarctic ones have been cold since they fell, but it would cost way too much to keep them cryogenic when they bring them back. So NASA stores them at room temperature, but in nitrogen cabinets to make sure that they do not interact with the atmosphere. And then when we request the small samples, we just keep them in desiccator cabinets, and they don't really react for the things we're looking at. So.
Yeah, the fact that you found benzene, which is a fairly complex molecule, have you looked also, I mean, how does this compare with the interstellar dust, the ISM? That's
a really good question. So we find, when I said most of the carbon, when I said benzene, what I mean is really these aromatic functional groups within the organics, and they really are like this organic matter seems to be made of sort of large graphite-like domains cross-linked with aliphatic things in a very complicated structure, which is in fact quite consistent in some ways with what's inferred for interstellar dust. And there was work from Yvonne Pendleton like 25 years ago that compared some interstellar infrared absorption spectra of interstellar dust, compared it to measured directly on the meteorite organics, and found a really good match for some wavelength bands. And that's an argument that it's quite possible that much of this organic matter is also pre-solar. And it was from the pre-solar molecular cloud. We just can't prove it at this point. It is my favorite explanation, but there are others that do not agree. And we've been fighting about it for a very long time.
Go ahead.
Oh.
Have you found nitrogen?
Oh wait, hold on one sec. He's gonna.
Have you found nitrogen in any of these?
Yeah, we find nitrogen in the organic, so it's organic nitrogen, usually in like
Okay,
nitrile.
is there any chance of, you know, being the prototype for, what do you call it, proteins or anything like that?
It's amino acids.
Amino acids are.
There are amino acids there
Amino
that
acids.
form from it. So in principle, yes, some of this material very well could have been precursors for the very earliest prebiotic molecules, organic molecules that became life on Earth. It's very complicated to work this out and very hard to tell, but that's part of the reason we study this stuff, is because there is potentially a direct connection.
If it wasn't complicated, you wouldn't have a job.
Exactly. And yeah, I mean, so one of the things that people will look for is, life on Earth is single chirality, right? It's if there are molecules that have a left hand and a right hand view, and everything on Earth uses the left hand form of these molecules, amino acids and things. But in meteorites, it's almost, most of the measurements show an equal amount of the left and right. But there's some reports of some molecules in the meteorites where there's a slight excess of left. So that is taken as proof that it came from this. But I think it's controversial enough, it's important enough and difficult enough measurement that people are always worried that, maybe there was some biotic contamination in the sample that added that slight left-handedness. But these are things we're trying to get at. Yeah.
Yeah, I've seen suggestions that here on Earth people could filter the water that comes and falls on their roof and comes down the drain pipe and get a sample of dust of some sort, and that some of them might be cosmic.
You can find micrometeorites in your gutters. It's very, very difficult. There is so much contamination, so much terrestrial dust, but people do occasionally find this. And there's a guy in Europe who wrote a book last year on micrometeorites, and he's devoted a lot of time to doing this, to finding ways to find them and going to people and setting up detectors on their roofs and then teaching them how to filter them. And he has a really nice book. I'm trying to remember what it's called, with these beautiful pictures of micrometeorites that he found in cities. But it's very, very hard.
Okay. And the second thing, I'm just wondering, since clearly, the dust cloud that formed our solar system was probably compressed and formed by dust put out by those AGMs and supernovas, they themselves are results of previous enrichments.
Yeah.
So I wouldn't think that each one of them would have the same isotopic mix.
They don't, and in fact, that's why the data spread out over many orders of magnitude. And in fact, one of the things we do look at is that some of the isotope ratios we measure, we do think do reflect different starting conditions of the stars. So we use them to kind of track out the chemical evolution of the galaxy, where we think this grain formed in a star that formed later than this one because they have a different silicon isotope composition. So we can disentangle to a large extent which isotope ratios are due to the nuclear reactions in the star itself and which predate the nuclear reactions in the star. We try to do this. It's all, you have to use a mixture of models and astronomical observations, and it's an iterative approach. But we think we have a pretty good understanding of a lot of the ratios, and that's a really good question. So we think we can trace back several generations of stars in the galaxy.
If there are no other questions, let's thank our speaker again.